Namaste and welcome to the lecture on linear algebra through geometry. In the last lecture we looked at the effect of the matrix A, a real symmetric matrix A on a vector. We found that it was basically projecting into orthogonal axis and scale the projections and sum them up, basically linear combination of projections onto orthogonal eigenvectors, that is what we had. We just have a small, there is a small thing that I wanted to add to it, we will do that and then we will get on with quadratic forms. So, that will be the agenda for this lecture. Okay. So, what we do is we are going to define a new term, we are going to call this as the spectrum. The spectrum typically is basically this typically the set of eigenvalues of A, set of eigenvalues of A is called the spectrum, and what we have is we have the idea of what is called as the spectral theorem. Spectral theorem, where it says that a real symmetric matrix, real symmetric matrix A let us say n by n has the following properties. Namely, number 1, the number of eigenvalues, the number of real eigenvalues is equal to n. In this case we count the multiplicities also, number of real eigenvalues is equal to n, let us say counting all the multiplicities. The algebraic multiplicities. Then second one, so we have the what you call, we had the dimension of the eigenspace which was basically the geometric multiplicity, right. So, the dimension of the eigenspace for each eigenvalue lambda, is equal to the algebraic multiplicity of lambda, algebraic, that means you do not have a deficient or a deficit eigenvalue, algebraic multiplicity of lambda. Then we already saw that the eigenvalues, if they are distinct, then the eigenvectors are orthogonal. So, what we are going to say is the eigenspaces are orthogonal, the eigenspaces, or let me put it this way rather than this, let us take this up, the eigenvectors are orthogonal, the eigenvectors corresponding to distinct eigenvalues are orthogonal, are mutually orthogonal to each other, and then we have the last one, which is basically what it says, A is orthogonally diagonalizable. That means the P matrix, which is an orthogonal matrix, that we are going to use that for diagonalizing this A. So, A is orthogonally diagonalizable, and remember we also had this thing where we said that AX is equal to, for again real symmetric matrix A with distinct eigenvalues. Ax was basically what? Lambda x, lambda 1, u, let us take this as the vector u1, u1 transpose plus lambda 2, u2, u2 transpose plus etcetera plus lambda n, un, un transpose into x, where u1 is basically an n component vector, and in fact I will say every ui is an n component vector. So, if I say u1, it is basically the n component vector, they say u1 is equal to u11, u21, u31 etcetera un1, right. So, this is how it is going to be. So, any ui I can write this as ui is equal to u1i, u2i, u3i, uni, it has n components. So, A is equal to sigma lambda I ui ui transpose I is equal to 1 to n. This is basically called as the spectral decomposition of A, spectral decomposition of A. We will see a similar result when we do singular value decomposition too, spectral decomposition of this A, because you are trying to break this matrix A into let us say the you are going to express this matrix A in terms of unit rank matrices or rank 1 matrices, and those pieces are basically defined by the spectrum corresponding lambda i's. Is that clear? And we see that ui transpose is basically a projection matrix. Now, with that what we do is we get on to the next topic which we want to do, that is basically the quadratic forms. We are going to look at quadratic forms. Now, what do we mean by quadratic form? We will just take a simple example. Let us say we have this for a pair of numbers, let us say x1 x2, pair of numbers, let us say real numbers x1 x2, we define this, we define let us say h of x1 comma x2, which is nothing but let us say a x1 square plus 2b x1 x2 plus c2 plus c x2 squared, right. So, what we say is h of x1 x2 is basically a quadratic form. Now, interestingly, this can be captured in terms of matrix operation. Let us look at that. So, what do we have? Let us look at this. So, we had this h of x. So, I basically had this h of x1 comma x2, which was nothing but a x1 square plus 2b x1 x2 plus c x2 square. Now, I can capture this as let us say a x1 plus b x2 b x1 plus c x2 into let us say x1. Basically I will do a dot product of x1 with x1 x2. What am I trying to do? I am just going to look at the dot product of this. So, this is going to be x1 x2 So, if I take this is a vector, let us call this as vector v u, and let us call this as vector v. So, u dot v is nothing but v transpose u. So, I am going to have x 1 x 2 transpose, that is basically the transpose of this vector v, and I am going to have a x 1 plus b x 2 b x 1 plus c x 2. Now, this I can write it again as x 1 x 2 into a b b c into x 1 x 2. So, what are we going to say? We are going to say that the quadratic form. So, we are going to say the quadratic form h of x 1 comma x 2 can be written as x transpose a x, where x is equal to x 1 x 2, a is equal to let us say a b b a. We again see the symmetric matrix coming into picture here, and we are going to this is what it is. So, the matrix A is going to be called as matrix A is called the matrix of the quadratic form. It is called the matrix of the quadratic form. Right. This is called the matrix of the quadratic form. Now, let us look at something interesting here. Say suppose I have, say suppose we have say the vector x is equal to x 1 x 2. This vector x is basically obtained as a transformation of this vector, let us say y, by a matrix P. That is, I am going to have a matrix P, and I am going to say this is y 1 y 2. Now, what do we have? We have the quadratic form, which is basically the quadratic form of x that we saw is going to look like this. So, we are going to say quadratic form of let us say this vector x, x 1 comma x 2 is nothing but we had x transpose a x. Now, x is nothing but p y. I am going to put this as p y transpose a, and then I am going to have this as p y. So, this is nothing but y transpose p transpose a p y, right. So, we are going to have this is going to be p transpose y transpose p transpose a p y, right. And let us say p is basically an invertible transformation, that is more important, it is invertible. Therefore, I can get y is equal to p inverse x, right. So, now what we see is we have, by change of variable, what we have done is we have basically we are looking at another new matrix, which is going to be the quadratic form, which involves this variable v. So, what we are going to say is the new matrix of the quadratic form is p transpose a p, right. We know that we already have taken A to be a symmetric matrix. So, we know that A is symmetric, recall A is symmetric. What do we have? If A is symmetric, then what happens? We can find orthogonal matrix. This implies we have an orthogonal matrix P such that P transpose A P is the diagonal matrix D. If you recall, we will just do this, recall for real symmetric matrix A, we have A is equal to P D P transpose, D is therefore what is D? D is nothing but P transpose A P. So, if I multiply this by P transpose, so I get P transpose A is equal to P transpose P d P transpose. So, P transpose P is identity matrix, then I have d P transpose, post multiply by P I get P transpose P, that is again identity matrix. So, I get D is equal to P transpose A P. So, which implies this fact tells us that Y transpose P transpose A P Y can be actually written as. So, let us do this. This implies Y transpose P transpose A P is now equal to Y transpose diagonal matrix into Y, right. This is what we have, right. So, we have certain ideas about this what would we call, okay. We have certain names for these matrices for which depending on what is the value of this x transpose A x, what does that boil down to. So, based on that we have matrices which we call it as positive definite, positive semi definite and so on. Let us look at that definitions in some time now, okay. So, there is what we have is, what have we seen? We have your quadratic form which is going to be just in terms of your diagonal matrix. So, I am going to define a new thing which is basically called as the principal axis theorem, principal axis theorem, which says that let A be a real symmetric matrix I have already used A as R n by n. So, I can actually remove this real because it is already going to contain real value. So, I will say let A n by n be a symmetric matrix. Symmetric matrix then what it says is, then we have an orthogonal change of variable, we have an orthogonal change of variable let us say x is equal to p y, that transforms the quadratic form, x transpose A x to y transpose d y. Now, what is so special about y transpose d y? That is something which we want to explore. So, let us do that and then come back to fill the gap that we have. So, what is y transpose d y? Let us look at this. Let us just take y 1 y 2 and let us say d 1 0 0, okay, let me make the, okay, and d 2 and or let me make this as say some, okay. Let me take this d 1 and d 2 itself and what I have is y 1 y 2. Now, what do we have? This is equal to y 1 y 2 into d y 1, I mean d 1 y 1 d 2 y 2, right, d 1 y 1 plus 0 y 2 0 y 1 plus d 2 y 2. So, I am going to get this which is nothing but d 1 y 1 squared plus d 2 y 2 squared. What was the original quadratic form that we had x transpose A x, basically we had A1 I mean A x1 squared plus 2b x1 x2 plus c x2 squared. Now we had this cross term, and by this orthogonal transformation or the orthogonal change of variable, what did we do? We came out with a quadratic form wherein which the cross product term vanishes. So the principal access theorem simply says that if you have a real symmetric matrix, then you have an orthogonal change of variable y is equal to I mean x is equal to p y, such that x transpose A x gets transformed to y transpose dy, which basically is devoid of your cross terms. That is more important. This cross term will always give a problem. So we want to eliminate this cross term, so that that can be done by taking this orthogonal transformation. So what are we going to say? We are going to say y transpose dy with no cross term. Yeah, okay. So we have certain classifications of this quadratic form. So let us look at this. A quadratic form basically you can classify your quadratic form to be I mean positive, definite, that is what I am going to do. So let us look at that. A quadratic form Q is called 1 positive definite if q of x is strictly greater than 0 for all x not equal to 0, and remember this x that I am talking about is basically the n component vector x1 x2 xn, right. So I will write this as q of x for x not equal to the 0 vector. The second one we are going to say negative definite if q of x is less than 0 for all x non-zero vectors x. Third one is basically what we call as indefinite wherein which q of x assumes both positive and negative values. And there is something more, we are going to say this for positive semi definite if q of x also takes the value 0. So we say that q of x greater than or equal to 0, we have negative semi definite if q of x is less than or equal to 0. True for again for all x vectors, for all x vectors, right. Okay. Now we captured this quadratic forms in terms of the matrix. We said that the matrix associated with the quadratic form or the matrix of the quadratic form was basically the symmetric matrix A. So what are we going to do is we are going to look at the quadratic forms through the eyes of symmetric matrix and the eigenvalues of the symmetric matrix. So, we are going to look at that now. So, what we say is if A, so let us do this, let A be any real symmetric matrix let A be any real symmetric matrix, then the quadratic form X transpose A x X transpose A x is 1 positive semi definite or positive definite if the eigenvalues of A, if the eigenvalues of A are all positive. B, negative definite if the eigenvalues are all negative. Three, indefinite if A has both positive and negative eigenvalues. Okay. Now, before we even go further, let us see if you have seen this kind of a quadratic form somewhere else before. Have we come across this before? Of course, we did come across this when we looked at the length of the vector. Let us look at, let x be a vector in Rn, be a vector in Rn. Now, what is the squared length of this vector? This is nothing but x transpose x, which is nothing but x 1 squared plus x 2 squared plus etcetera plus x 3 squared plus x n squared. And now what did we say? We said that this is equal to 0 if x is the 0 vector, it is greater than 0 if x is not the 0 vector. That means, we already have a quadratic form here which says x transpose, I will put this as identity matrix X. So, which means we have already seen this idea of our quadratic form beforehand itself, right. Now, let us try to look at this eigenvalue and try to prove this, and then let us look at this. So, proof that, what is the proof for? This proof is basically for this in terms of the eigenvalues, positive definite in terms of the eigenvalues. So, we are going to look at the proof for this. So, what do we have? We already saw the principal axis theorem. So, we can do this for a real symmetric matrix A, for a real symmetric matrix A, by the principal axis theorem. We have an orthogonal change of variable x is equal to p y such that the quadratic form of x can be written as x transpose A x. I can write this as y transpose d y, which is nothing but lambda 1 y 1 squared plus lambda 2 y 2 squared plus etcetera plus lambda n y n square, where lambda 1 etcetera lambda n are the eigenvalues of A, eigenvalues of the real symmetric matrix A. Okay. Now, if you see that since we have the matrix P to be invertible, there is going to be a one to one correspondence between all non-zero x vectors to all non-zero y vector. So, what we do is basically what we say is, you can look at that if you have q of x which is equal to x transpose A x which is equal to y transpose d y, you have sum of this, you have y 1 square, y 2 square, y n square, all of them are going to be either 0 or positive numbers, and therefore, this quadratic form is now being controlled by the signs of the eigenvalues which are basically lambda 1, lambda 2, lambda n, right. The components these are all squared terms which will all be positive or 0. Now, what happens? The sum is going to be controlled by the signs of lambda 1 and lambda 2 etcetera. Suppose if all the lambda values are positive, then we are going to say that q of x is positive definite, and if lambda 1s are all negative, we are going to say that q of x is negative definite, and if you have a mix, then you say that q of x is basically indefinite. Is that clear? So, that is basically what the what you call the quadratic forms and all those things. We will see that the applications of this, I mean many of the least squares approximation that we did also involves our quadratic forms and so on. So, most of the constraint optimization problems that you would see, that we would encounter, will typically involve this quadratic forms and so on. So, in this module what we have studied is, we have basically looked at the idea of real symmetric matrices. We have looked at the properties of real symmetric matrices in terms of its eigenvectors, in terms of its eigenvalues, in terms of orthogonal diagonalizability and all those things. In fact, real symmetric matrix is you can always say that it is always diagonalizable and stuff. So, and also we looked at the idea of this quadratic forms, and we looked at positive definite, positive negative definite and so on from the eigenvalues of the real symmetric matrix. So, if you have a real symmetric matrix, then you can do a lot of things about it, and we also know that what do you say, our variance covariance matrix is a real symmetric matrix. In fact, we will see that the variance covariance, if for any matrix to be what do you call qualify, for any matrix to qualify as a variance covariance matrix, in your stats you will see that the variance covariance matrix must be positive semi definite. So, that is these are things that you would actually look at. So, there are various applications. Some of these applications we will also look at it in the subsequent modules, where we are going to talk about applications of linear algebra. So, overall what we have covered in this module is about real symmetric matrices, properties, and spectral theorem we did. Then we also looked at principal axis theorem, and we also looked at certain properties of real symmetric matrices, like the eigenvalues are always real and so on. And finally, we got on to the notion of quadratic forms, which is also going to look at I mean for which you have a lot of applications, which we will see in the later modules. So, in the last few modules we have been looking at generalizations of our whatever that we had studied in 2D, 3D. We went to the vector spaces, we associated matrices, I mean vector spaces with matrices, then we looked at orthogonal complement subspaces, we looked at invariant subspaces and all those things, and finally we have come to the idea of real symmetric matrices and applications. In the next module we will look at singular value decomposition, followed by applications of linear algebra. Thank you.